problem, but here is an example that I believe is going to be very helpful for our final and preparing for the final. And in this particular example, I'm giving two sections of transmission line. This one here, one, and then the second is this one. There is a load at the end, which I call it like the antenna radiation resistance, because if you connect an antenna to, say, a transmission line, and that has a radiation resistance of 250 ohms, that means that all of the power that goes to this resistor, then it is radiated. That's why it's called radiation resistance. And then in this problem, as I describe it here, we have to match the antenna to the source. And in fact, in the process of doing that, I am asking you to create this type of matching network. So what you do is that you have, starting from the antenna, to go back by a distance, D1, and then place there, that's what the problem is asking. Is asking you to place a shunt or a parallel stub, which is this purple one here, which is open circuited at the end. All right, and they tell you that what you have to do is the characteristic impedance in every section of transmission line, including the stub, has to be Z0, which is the same with the internal impedance of the source. And then we give here that the internal impedance of the source is 50 ohms, all right? And also there is another constraint in the problem. It says, assume that the distance between the source and the antenna is one wavelength. So you assume that between this point, AA prime, and this point, CC prime, you have one lambda. You're restricted by that. And is asking then to, another constraint is that D1, which is the distance where you place the stub from the load, from this antenna, it has to be less than a quarter of a wavelength. So there are constraints there, all right? So the total, the distance between the source and the antenna is one wavelength, and this D1 has to be less than a quarter of a wavelength. So here, and then they're asking questions. I could give that in the final. It says the first question is find D1, D2, and D, which is all of the lengths of those transmission lines and the stub. And it is asking you to find them so you have the maximum power transfer from the source to the load. All right, and assume here that the maximum value of the source is 1 volt vis a vis. Then we have to find the power radiated by the antenna. And then we have the third question is to find the VSWR on all sections of transmission lines, including the stub. Okay, so here is what I did. In fact, I did this so there is no confusion about where we are looking at what we're doing. At least in the beginning, it will be important to be that detailed on how you show the connections here. Eventually, you don't have to do this kind of, detail. But what I decided to do, and I will probably do the same thing for your exam, is to show what is the first section of line and name the input and output ports, and then show this part of section of line and name also the input and output ports, and then also name separately the input and output ports of the stub. But what I will do in the problem, as I said in class, I'm gonna give points for redrawing the, on your own, copying the figure and drawing it. So you pay attention to what is given and what are the dimensions that are unknown and we have to specify. So here, for example, it becomes easy to see that we have to specify D, D2, and D1, that from AA prime to FF prime, that we have 1 lambda, the D1 has to be less than 1/4 of a wavelength, and the stub is open circuited. So here, the next thing that I said we have to do is to write what is given to us and what we need to find. So the first thing is 50 ohm, characteristic impedance everywhere. The radiation impedance of the antenna is 250 ohms. D1 is less than 1/4 of a wavelength. The total distance, in fact, I should not probably say that. Let me correct this. The total distance between AA prime and the total distance between AA prime and FF prime is 1 wavelength, not D. Visa base is 1 volt and stub is open circuited, which means that at the end of the stub, like here, practically your load is infinite for an open circuit. And what we have to find is D1, D2, and D, and to find the power radiated by the antenna. All right, so to find all of the dimensions, before we go to the Smith chart, you will have to look at the problem and make an observation. The important observation here is that the stub is in parallel. So we have to transform all impedances to admittances. This is what I also said on Wednesday. And on the recorded lecture on Friday, you have to remember that if the stub is in parallel, everything has to be transformed. All of the impedances have to be transformed to admittances. If I were to do that, then you see what I'm doing here. All of the characteristic impedances, I make them characteristic admittances. I make the load an admittance, and then every input, instead of an input impedance, for example, at BB prime, I write input admittance. Instead of an input impedance at EE prime, I write an input admittance here, all right? And also I calculate that the characteristic admittance is the inverse of the characteristic impedance. So it's 1/50, which makes it 0.02 1/ohm. So the second thing, after we make that observation, the second thing is to be able to use the Smith chart, we have to normalize all admittances. But when we normalize admittances, we normalize them with respect to the characteristic admittance there. So now we normalize this radiation conductance. We have changed it, obviously, with respect to Y naught. And then that gives us this number, all right, for the normalized conductance. And then what we do is, I need to remind you, we normalize the GA and then we find it on the Smith chart. So I'm going now to the Smith chart here, and we find where GA is. GA normalized is a real number. There is no imaginary component, which means that at this point, as I show, is going to be here. In fact, let me see, if you look at this, it has to be 0.02 or 0.2, excuse me, and then it's right here. So you look along the horizontal axis, and you find that is at this point here. Okay, from there, then we know that we have to move from the load towards the generator and find until we find where we are gonna include the stub. All right. First of all, one thing, to move from your antenna, which is here at this point, to move from your antenna towards the generator, you have to move on the constant VSWR circle, which is this one. All right, you see it's a circle that has the center at the center of the Smith chart, and the circle goes through this point, which is the normalized conductance. So you write this circle, which is this red circle. You write it, you draw it rather, okay? And then you know that you have to move towards the generator. This is the direction. You have to move along this direction, all right? I mean, from like clockwise, okay? But where you're gonna stop, to be able to understand at what point you're gonna stop, now you go to this figure here. Okay, so I am right here, which is at this point, as you see, it is not normalized, or we can make everything normalized. And if we do, if we keep it normalized at this point, it's gonna be 0.2. Okay, and then this is gonna be normalized. And this is, and then this is the, this is gonna be normalized. And I keep there, why not? I mean, this is just to remind us that the characteristic impedance is why not? But now you need to remember that we are moving on the Smith chart from the antenna, which is here, we are moving towards the generator along that direction. And we have to stop somewhere and place the stop. So we have to move from F prime, we have to move to E prime, okay. If we stop, still we don't know how much it is, how far it is. If we stop at this point, then we can replace this red transmission line by its equivalent input admittance, which is here. And you at E prime anymore, instead of the transmission line, you're gonna have an equivalent input admittance, which is here that you see. And at that point, we have to place a stub with an equivalent input admittance here, so that the input admittance we see from here, like this one, it has to be equal to 1, because that's what matches at this point. It creates a perfect match to your transmission line, all right? So the condition for a perfect match at this point, BB prime, for everything that happens before it, is that the sum of these two here, these two admittances, the sum of these two admittances, because they are in parallel, all right? And that's why we have to move it to admittance, because the Smith chart can only add things. The Smith chart cannot give you the combination, the parallel combination of two impedances. It can give you the parallel combination of two admittances. It cannot give you the series combination of two admittances. It can only give you the series combination of two impedances, all right? So if we add a stub in series or anything in series, if we add anything in series, then we use impedances. If we add anything in parallel, we use admittances. So this one, it has to be equal to 1, the total. And from there, if we know how much this is, then practically we can find that one. Now, what is characteristic is for the sum of the two to be equal to 1, since this is a stub here and it's only reactive, meaning it's only imaginary, that implies that the real part of this has to be 1. That now takes us up here. And then what it tells us is when we start at FF prime here, that's where our load is. Our load is right here. When we start there, we move along the red circle clockwise until we find the circle that takes us to the center of the stub and to the center of the chart. And the circle who takes us to the center of the chart, okay, move it here. The circle who takes us to the center is this one. Okay, so practically we move along this circle. As you can see, the purple arrows, and then that takes us to the center of the chart. And at that point, practically, we are at point B prime, which is in fact where we have achieved a perfect match, because this only at this admittance here, normalized is equal to 1. All right, so arriving at the center of the Smith chart shows you that you have been able to achieve a perfect match. Okay, so practically that what I just explained, it says that this point here is at the center of the Smith chart. When we are done with the matching, then this impedance here, normalized, is at the center of the Smith chart. Okay, so now we have to find out how much is this normalized impedance that is in fact the input impedance from this section of the transmission line. To find that, this impedance is right here, admittance rather. This admittance is right here, all right? And I have indicated how much this is. How do we find that? We measure it. So from this chart, so from the real part is what goes on this circle, as we said, and the real part is 1. And the imaginary part we find from E prime, that from this point there, that I call E prime, you find the other circle, this one, okay, that really shows you along which path all of the points have the same reactance. And what we go and measure here, and we see 1.8. So practically the value for the normalized admittance at this point is 1 plus J 1.8. Okay, so we found that. So now we go back to this equation we had. We plug here for this 1. Well, first of all, we are looking, did I say that? Okay, we found that. We are looking to now compute this value, and we write this as 1 minus this one. Okay, so since what I have highlighted here is 1 plus J 1.8, we subtract that from 1, and what it gives us is minus J 1.8, which tells us that the equivalent impedance of this stub has to be equal to minus J 1.8. So we found the equivalent impedance of the stub. Now, what we have to do is to find its length, okay? And from here on, we'll find all the lengths, as a matter of fact, that they're asking us. But let's start with the stub. So the stub, as we said, is open circuited. Open circuit in admittance form. So in impedance form, the impedance open circuit is infinite, the impedance of an open circuit, but the admittance of an open circuit is the inverse. So it's 0. It's right at that point. Then from there, we have to go until we find minus 1.8, because the stub has that as input admittance. And we find minus 1.8 there. And then we take 2 lines. We draw 2 lines, one that connects the center of the chart to here, and the other that connects the center of the chart to here, okay? So practically, the length of the stub is from this point, that I'm gonna write it, all the way until we come to this point. To move from here to there, we have to describe a whole half circle, which is equivalent to to a quarter of a wavelength. So let me see. This one is 0.25 lambda. And then up to here. And then from there, we have to move down to that point, which is here, let me see, point 0.34 almost lambda. So practically, and that is starting from 0, which is up here. So the length of the stub is, in fact, we don't even have to add anything. It gives us directly. So I will remove that so we don't get confused. So the length of the stub is 0.34 lambda. So that's how we find it. Okay, and then this one also, we don't forget that. This is the impedance, the admittance of the stub. Input, let's see, C prime. That's how we call that. All right, and that is the termination of the stub. Now, we need to go back. We found D2. We need to go back and find D1. D1 will do a similar thing. If you remember, when we moved from the end of the transmission line, the red one, until we found the position where we would place the stub, so we moved from here to here to find the length of how much we moved. So we draw these yellow lines as I did before. So this one, first of all, to connect the center of the chart to FF prime. And then this one, this other one, to connect the center of the Smith chart to E prime. And then we do the same. We start at 0 lambda, which is here. Then we read the distance here, which is 0.182 lambda. And therefore D1 is 0.182 lambda. Now, it's already less than a quarter. A quarter of a wavelength is there. So this is where a quarter of a wavelength is from the beginning. So here, this says 0.25 lambda. So we already satisfy the condition that D1 has to be less than a quarter of a wavelength. And we have found this abyss. Now, we have also been told that the whole distance between A prime, which is this one, and FF prime has to be one wavelength. Since we know D1, then we can find D, all right? So D, in this case, so practically, so here we can say that we have concluded from here, we have concluded that D2 is 0.34, okay, 0.34 lambda. And we have already found D1. So D here, which is that, is gonna be the whole distance AA prime, FF prime, so the whole distance between these two, minus D1. So it's gonna be, and therefore, and D is gonna be 1 lambda minus D1. Therefore, it's gonna be 1 minus 0.182 lambda. So it's gonna be 8 1, and then 8 of lambda. And then we found D. So as just to summarize everything, so the answer to the first question, to question 1, is the following. D is 0.818 lambda. D1 is 0.182 lambda. And D2 is 0.34 lambda. So that okay, I think we are saying, okay, there we go. And so it's this. Okay. The question now, there are 2 more questions, and then we'll go back to the beginning to see what the other questions are. Question 2, find the power radiated by the antenna, and then find the VSWR in all lines, all right? So therefore, let's go down here. And in fact, what we're gonna do is we are gonna move. We have a picture here. It's easy to see it, all right? So we'll look at this picture that we have, figure. And then so question 2, let me just write it a little better. 1 second. So question 2 here. Question 2. It asks us to find the maximum impedance from the impedance that goes to the antenna. But since the input impedance here, we found that this one here is equal to the characteristic admittance of the line. That means the Y input at BB prime, nothing else but the Y naught. And therefore, there is no reflection on this transmission line, which means that the input admittance here is also Y naught, all right? And therefore, we can rewrite now the circuit. If you like, you can keep it in admittance form, or you can keep it in impedance form. But let's assume that we will keep it in admittance form so we don't change very much. So here we are going to have the source. So we're going to have the source, V sub S. We are going to have the internal admittance of the source, Y naught. And then we're going to have here the impedance that the source sees at AA prime, the admittance rather, which is also Y naught. And therefore, the power that goes, if Vs is 1 volt, all right, then practically the power that enters AA prime, real power, is going to be 1/2 the voltage across AA prime times the current that flows here, I, and everything is going to be real because both Y naught there are real values, and therefore we write that, which means according to what we found before, it's going to be 1/2. The voltage is going to be 1/2 of Vs, and the current is going to be practically the current is going to be equal to, in fact, we have from Ohm's law, we will have that Y times Y naught is going to be VA prime. All right. So from the load, Therefore, the current here is going to be Vs over 2, and that divided by Y naught. All right, and that's going to give is going to be the power that goes inside the port AA prime, but since only the load G sub A, yeah, everything then is real goes to the load. So practically it's going to be Vs squared 8 Y naught. And that is going to be the power in watts that goes to the load. And therefore, that's the result for question 2. Question 3 asks then all the VSWRs. So let's see how we measure the VSWR. We'll go from here. VSWR, you remember we call this red circle the VSWR circle, and it's the circle for the red line for this one. So to measure the VSWR for that, we just have to draw this one. We draw a line from this point here, from the leftmost point on the horizontal axis that this circle has, and then we'll move it here. It has to be straight, all right? And then we are gonna go and look at the value of this one here. And it's a logarithmic, so it starts from this point and goes from 1 to infinity, very large values. So there we can measure, and the value is gonna be 4 point almost 5, oh no, 4 point something 4, maybe. So, oops. Okay, so that is gonna be 4 point, say, 4, and that's the VSWR. VSWR on the line that has length from, this is from EE prime to FF prime. Okay, that is the first VSWR. The so let's now solve, the easiest one is this one. Let me see, this. On this line, it's totally matched. There is no reflection. How much is the reflection coefficient? Excuse me, how much is, yes, let me start with that. How much is the reflection coefficient on a line that is totally matched? Is 0. 0, exactly. So here, for example, this is, let's put question 3 here. So then, as part of question 3, we have that the VS, let me see, okay, the VSWR between, we measured between the line, let's start with the line, EE prime, let's write that here, to FF prime is 4.4. Then the VSWR, the front line, since the reflection coefficient is 0, the VSWR is 1. Remember that? Always remember it, because the VSWR is 1 plus magnitude of gamma, 1 minus magnitude of gamma. If the reflection coefficient is 0, so VSWR is 1. Therefore, from AA prime to BB prime is 1. So the last question is, what is the VSWR on the stub, which is, let me make it here, stub. So here, let's see how much this is. The stub, you see, it's on this outer circle, because the stub does not have the load at the stub is infinite, all right? And so in impedance form, if it's open, in admittance form is 0, all right? And that means that the stub is always around the outermost circle. which is practically this one. The stub is gonna always be, because that's exactly where it's 0, all right? In the outermost circle from all of the resistive circles, let me see here. That's horrible. So let me do this one and then I will fix it when it gets here. There. Okay, close. This is the circle that corresponds to 0 impedances or infinite impedances, all right? So any stub, either if it's open or short in any form, impedance or admittance form, that's the circle that characterizes the stub, is the outermost circle. Therefore, to find the VSWR for that, you just draw this straight line from here. And if you see, the line goes to which value? Infinite. If we go here, the line for this one is here. So the VSWR for the stub, for any stub, short-circuited or open-circuited stub is infinite. You need to remember that. For any stub, the VSWR is infinite. For a matched line, which is this one here, the VSWR is 1. And that is here. And therefore, the only the line that it connects to the load has that VSWR. And with that, I think we have solved practically this problem. And I want to see if you have any questions about this problem before we go now to the solution of, to the homework, that you may have any questions.
I have a question.
Yes, go ahead.
Do we always draw the line from the left side of the circle?
Could you show me which line you're talking about? These lines, the line when we are looking to find the distance?
No, the VSWR line.
Yes, always to the left, exactly. Okay. You see here, there is only half. That's why it stops this, let me see. This one here, this line stops here, you see?
Yes.
Yeah, the reason it stops there is because that's where it only goes from the left side. Exactly, that's a very good observation. Any other questions about this? I will put those solutions also on Canvas. So if you go through the solutions, please, I will also go through the recording lecture as well, because it helps a lot of times. It will help you if you don't understand something. Any more questions on this? Let me see. Okay, so if not, what I will do is I will stop sharing for a second. Okay.